Roger Pielke Jr.'s appallingly bad analysis of billion-dollar disasters. I'm Blair Fix. According to a simple linear trend, losses per disaster are down by about 80% since 1980 as a proportion of GDP. Roger Pielke Jr. In the world of scientific disinformation, Roger Pielke Jr. is a well-known player. A political scientist by training, Pielke has a long history of being a thorn in the side of climatologists who study natural disasters. Pielke's latest entry in this genre is a 2024 paper called Scientific Integrity and U.S. Billion-Dollar Disasters. The paper takes aim at the billion-dollar disasters dataset run by climatologists at the NOAA. As the name suggests, the database tracks the cost of U.S. weather and climate-related disasters, which have inflation-adjusted losses that exceed $1 billion. Or rather, the database tracked these costs. The billion-dollar disasters database was recently canceled by the Trump regime. Afterwards, Pielke took to his blog to celebrate. Now, my goal here is not to defend the billion-dollar disasters dataset from Pielke's criticism. Instead, my aim is to show that Pielke's analysis is so flawed that it undermines his own appeal to scientific integrity. For his part, Pielke claims that putting climatologists in charge of disaster loss estimation is, quote, problematic, and that the job would be better left to, quote, proper economists. Furthermore, Pielke argues that the billion-dollar disasters dataset is so faulty that it violates the NOAA's own standards on scientific integrity. Yet while Pielke sits on this high horse, he manages to so horribly botch his own analysis that one wonders if he is unintentionally writing satire. In what follows, I'll spend a whole essay unpacking and debunking a single chart. Figure 1 shows Pielke's published analysis of the billion-dollar disasters dataset. The graph seems to show a steady decline in average disaster costs as a share of U.S. GDP. The implicit message is that when climatologists warn about worsening natural disasters, they're overreacting. If anything, economic growth seems to be making disaster costs more trivial, or so Pielke claims. In reality, Pielke's chart reveals something quite different. It demonstrates that he doesn't understand the data he purports to analyze. You see, the trend line in Figure 1 has nothing to do with natural disasters themselves. Instead, it's generated by a series of mathematical artifacts introduced by flawed methods. The first artifact is created by Pielke's uncritical analysis of the billion-dollar disasters database itself, a database which is defined by a billion-dollar threshold. Unbeknownst to Pielke, this threshold creates an artificial skew in the disaster data, skew which makes it appear like average disaster costs are decreasing against GDP. On top of this threshold effect, Pielke then adds a distortion created by botched inflation adjustment. He warps history by using conflicting price indexes. Next, Pielke forces his stack of artifacts through an inappropriate linear regression, which both straightens the line but also, paradoxically, renders it statistically insignificant. He then finishes the job by not reporting his insignificant p-values, misindexing his GDP data, reporting data sources that are at best incomplete, and mislabeling his y-axis. In short, while Pielke's paper waxes about scientific integrity, his published analysis serves mostly to undermine his own credibility. With scientific integrity in mind, here's the road ahead. We'll begin with the pitfall lurking within the billion-dollar disasters dataset, which is the billion-dollar threshold itself. We'll see how this threshold creates measurement bias, and we'll look at ways to deal with the problem. Then, just when the disaster data is getting interesting, we'll throw it away and retrace Pielke's steps to producing Figure 1. Finally, once we've reproduced this comedy of errors, we'll reflect on the lessons learned. The billion-dollar threshold. Any analysis of the billion-dollar disasters dataset must grapple with a subtle but severe problem, which is that the database is defined by a dollar-level threshold. It records the costs of U.S. weather and climate-related disasters with inflation-adjusted losses that exceed $1 billion. Now, this $1 billion threshold makes for great PR, since everyone knows that $1 billion is a big number. But press releases aside, the $1 billion threshold is actually a burden for doing accurate analysis. The issue is that when it comes to natural disasters, what ultimately matters isn't the dollar value of disaster costs. What matters is disaster solvency, the scale of disaster costs relative to income. If disaster costs rise, but income rises faster, then there's no problem, at least for humans. But if disaster costs rise faster than income, the pattern points towards insolvency. To his credit, Roger Pielke Jr. recognizes this issue, and he recommends a solution with which I agree. To put U.S. disaster costs in the context of solvency, we should compare them to U.S. aggregate income, i.e. GDP. As such, the road ahead looks straightforward. First, we peg billion-dollar disaster costs to U.S. GDP. Then we look at the results. Easy. Except not. The issue is that when we place the billion-dollar disasters data in the context of GDP, the data set itself creates an artificial trend over time. If we're not careful, we might mistake this artifact for something real. Figure 2 demonstrates the problem. Here, I've taken the most recent version of the billion-dollar disasters dataset and measured the nominal cost of each disaster as a share of U.S. GDP. Each blue point is an individual disaster. The database pitfall lurks at the bottom of the figure. Looking at the red curve, notice that there are no disasters below it. This absence is by design. That's because the red curve represents the billion-dollar threshold used to define billion-dollar disasters. By definition, a billion-dollar disaster can't sit below this value. Now, the problem is that when this ostensibly fixed threshold is indexed to the consumer price index and then pegged to US GDP, it heads south with time. This movement, in turn, creates a skew in our disasters data. If we're not careful, we can mistake this artificial skew for a real-world trend. For example, consider the average cost of billion-dollar disasters as a share of US GDP. In 1980, losses from billion-dollar disasters averaged about 0.13% of US GDP. But by 2024, average losses had declined to 0.023% of US GDP, a roughly five-fold decrease. Although seemingly impressive, this decline is driven by a threshold effect, which makes a simple average misleading. The effect is similar to a university which gradually admits students of lower caliber, causing the average GPA to decline with time. While this pattern is real in a statistical sense, it says nothing about the student population at large. It's purely an artifact of the university's admissions criteria. In much the same way, the billion-dollar disasters dataset has gradually and unknowingly changed its admissions criteria by including disasters with lower and lower costs as a share of US GDP. The consequence is that average disaster losses appear to decline against GDP. But like our decreasing student population, this apparent decline is a selection effect. It says nothing about the population of real-world disasters. Looking ahead, Roger Pielke Jr. mistakes this billion-dollar threshold effect for a real-world trend in disaster costs. And from there, things only get worse. A constant solvency threshold. We'll get to Pielke's cascade of errors in a moment, but first we should analyze the billion-dollar disasters data in a way that avoids the threshold effect. Given the bias created by the billion-dollar threshold, there are two ways to deal with the problem. The best solution would be to order a whole new disasters database, one which lacks a cost threshold. The catch, of course, is that loss estimates almost always come with some sort of threshold, since government budget constraints and data limitations make it difficult to accurately track the losses from all disasters. So the question is not if there's a cost threshold, but what this threshold should be. On that front, the second solution to the threshold problem is to introduce a new threshold, one which is fixed against GDP. In other words, we cull the billion-dollar disasters data using a constant solvency threshold. Figure 3 illustrates this solvency approach. With our set of billion-dollar disasters, we exclude those that sit outside the red shaded region. The goal here is to keep disasters with losses that exceed a specific fraction of US GDP. In this case, I've chosen a solvency threshold of about 0.008% of GDP, as indicated by the dashed red line. Given this solvency threshold, we exclude disasters that sit below it, and we exclude disasters to the left of the red box. We do so because in these years there's the potential for missing data. Let me explain. When the original billion-dollar threshold sits above my new solvency threshold, a disaster might have losses that exceed the solvency threshold, but which do not exceed the original billion-dollar threshold. Such a disaster would therefore be absent from the existing billion-dollar disasters database. If we want to avoid this missing data bias, we need to exclude years when the billion-dollar threshold exceeds the new solvency threshold. Now, I should acknowledge that this culling procedure is in some sense arbitrary. Just as there's no scientific meaning to a loss threshold of $1 billion, there's no scientific meaning to my solvency threshold of 0.008% of GDP. I've chosen this value because it's functional. It culls the billion-dollar disasters database without throwing out too much data. An honest appraisal of natural disaster trends. With our culled billion-dollar disasters dataset in hand, our first step will be to give the data an honest appraisal. Perhaps the most pressing question is the trend in disaster solvency. If we sum the annual disaster costs in our culled dataset, how do they behave against US income? As Figure 4 indicates, there's tentative evidence that disaster costs are rising with time. Now, I'll be the first to admit that this upward trend is not particularly compelling. The regression p-value is 0.06 and the r-squared value is 0.09. That said, even the hint that disaster costs are rising against income should give us pause for thought. One of the great themes of the Industrial Revolution has been humanity's rising power over the natural world. Once the pawns of nature, now we're the gods. As such, it seems like our technological prowess should isolate us from the costs of natural disasters, making these losses increasingly trivial. Yet, judging by the pattern in Figure 4, the evidence cuts, tentatively, in the opposite direction. Actually, the evidence for worsening natural disasters is more compelling than I'm letting on. That's because one of the features of natural disasters is that the loss data is incredibly noisy. The reason is straightforward. Annual disaster losses are dominated by rare but calamitous events. For example, a massive hurricane hitting a big city. See the appendix for details. Since these calamitous events are unpredictable, the effect is that total disaster losses vary wildly year to year. Against this short-term noise, a subtle trend can easily get swamped. To separate the noise from the signal, let's take our culled billion-dollar disasters data and measure the trend in average losses per disaster. Or rather, we'll measure the lack of trend. As Figure 5 illustrates, when we peg average annual disaster losses against US GDP, there's plenty of short-term noise, but no hint of a long-term trend. The message in Figure 5 is that the average severity of big natural disasters is essentially unpredictable. It's a game of roulette played between humans and the gods of weather. Still, the game doesn't leave everything to chance. In fact, if we ignore the severity of big disasters and instead count their frequency, we see a clear pattern over time. Figure 6 runs the numbers. Here, I count the annual number of disasters in my culled billion-dollar disasters database. To reiterate, these are disasters with losses that exceed 0.008% of US GDP. It seems that the frequency of these big disasters is rising with time. Now, if this essay was about good science, I'd pivot here and ask a bunch of questions. First, is the pattern in Figure 6 robust? Are big natural disasters becoming more frequent everywhere? Or is the pattern unique to this particular dataset? Supposing that the pattern is robust, I'd then want to understand the cause. Now, the obvious culprit is climate change, which is likely making weather more volatile. But another plausible culprit is the nature of modern capitalism itself. You see, in recent decades, investors have turned to real estate as a place to park their money. As a consequence, house prices have steadily risen against income. Now, if property values are rising against income, it follows that property losses might also rise. As such, the rising frequency of costly natural disasters could be an artifact of modern investment patterns. Having piqued my interest, I'm now going to pivot and not investigate these questions. And that's because this essay is not about good science. It's about the error-riddled work of Robert Pielke Jr. Fooled by a mathematical artifact. To situate Pielke's analysis of the billion-dollar disasters data, it's helpful to first describe the broader landscape of climate change science. Throughout most of the terrain, we find natural scientists. These are folks who are trained in the scientific method and who genuinely want to understand the potential impacts of climate change, good, bad, and ugly. As we continue across the terrain, we find a small but vocal tribe of academics who call themselves climate economists. These are folks who masquerade at doing science, but whose job is mostly to run interference for business interests. For example, when natural scientists find a pattern that looks bad, the climate economists step in and manipulate the data until it confesses to a better story. For details about the sorry state of climate economics, see Steve Keen's work. As I see it, Pielke's analysis of natural disasters fits into the climate economist camp. Unlike a climate crank, Pielke doesn't spout complete bullshit. He analyzes real data, and he finds reproducible patterns that emerge from this data. But curiously, these patterns seem to always tell a happy story. Pielke's analysis of the billion-dollar disasters data is a case in point. He finds a trend which is real in the sense that it can be reproduced from real data, and the trend is also a happy one. It suggests that natural disaster costs are decreasing against income. Unfortunately, in his rush to spread good news, Pielke ignores Richard Feynman's first principle of science, which is that A, you must not fool yourself, and B, you are the easiest person to fool. Here's how Pielke gets fooled. Although Pielke is critical of the billion-dollar disasters dataset, he doesn't analyze the data itself with a critical lens. Seemingly unaware of the billion-dollar threshold problem, discussed above, Pielke naively takes the whole billion-dollar disasters database and dumps it through a simple average. Out pops the good news, which I've visualized in Figure 7. When we measure the average annual cost of billion-dollar disasters, we find that the losses have steadily declined against US GDP. Note, Pielke uses a different version of the billion-dollar disasters dataset than the one I've used here. I replicate his exact results in the appendix. Although seemingly convincing, the trend in Figure 7 has a slight problem, which is that it has nothing to do with real-world natural disasters. Instead, the downward trend is entirely an artifact of the billion-dollar threshold, on which the disaster data is based. Figure 8 illustrates the principle. Here, the red line shows the trend from Figure 7, the downward pattern in average disaster costs as a share of US GDP. Next to this trend, the blue line shows the billion-dollar threshold used to exclude disasters from the billion-dollar disasters database. When we tie this billion-dollar threshold to the consumer price index and then peg it against US GDP, the threshold moves south with time. Indeed, it moves south at the same rate as the apparent trend in average disaster losses. This similarity is no coincidence. It's cause and effect. When we peg the billion-dollar disaster data against US GDP, The role of the actual disaster costs is to provide statistical noise. When we then feed this noise through a threshold that moves relative to GDP, it introduces a skew in the data. Finally, when we run a regression on the skewed data, we get back a rescaled version of the billion-dollar threshold itself. In short, the trend line in Figure 7 tells us nothing about natural disasters. Instead, it circuitously tells us what we already knew, that the billion-dollar disasters dataset is defined by a billion-dollar threshold. The plot thickens. Backing up a bit, note that the regression line in Figure 7 has a p-value of about 0.06. Now, since the trend in the data is itself a statistical artifact, so too is the p-value. Still, if we mistook the trend line for a real-world pattern, then the high p-value would be a problem. It would suggest that the decline in average disaster costs is statistically insignificant, which means we shouldn't make much of it. Here's where the plot thickens. Pielke does make a big deal about the downward trend in average disaster costs, but his underlying regression is not statistically significant. See the appendix. So how did Pielke slip this contradiction past peer review? Simple. It seems he didn't report any p-values. Here the plot gets even thicker. Pielke could have published a statistically significant pattern had he run the correct regression, but this significant pattern is itself created by a second mathematical artifact which distorts the first mathematical artifact on which Pielke's results are based. This comedy of errors is what I mean when I say that Pielke's analysis resembles satire. History adjusted. Continuing to reproduce Pielke's work, our next step will be to understand his second mathematical artifact, which is created by the use of conflicting price indexes. The effect of this artifact is to steepen the downward trend in average disaster losses, thereby making the regression statistically significant. In my mind, this price index distortion needs some explanation to be comprehensible. As such, I'll begin with a brief tutorial on how mismatched price indexes can be used to rewrite history. Let's start with some hypothetical facts. Suppose that in 1980 my annual income was $10,000, and suppose that I used this income to purchase a car that also cost $10,000. While these dollar values are themselves historical facts, they're not meaningful on their own. What gives them meaning is their relationship. The fact that in 1980 my car purchase represented 100% of my annual income. Now, the thing about historical facts is that, assuming they're accurate, they shouldn't change. So regardless of how we study history, we should always find that my 1980 car purchase represented 100% of my 1980 income. Having started with clear thinking, let's now introduce some confusion courtesy of mainstream economics. Hold on, economists say. If we wish to study historical prices, we must adjust for inflation. Bowing to economists' authority, we decide to look at my 1980 car purchase through an inflation-adjusted lens. To do that, we adjust the 1980 dollar values to reflect modern prices circa 2025. We use the Consumer Price Index to adjust the value of my car purchase, which gives a modern price of about $4,600. And we use the GDP deflator to adjust my income, which gives a modern value of about $33,800. Why are we using the GDP deflator here? Well, because my income is a metaphor for GDP, which is implicitly indexed to the GDP deflator. Having dutifully adjusted for inflation, we once again calculate the cost-to-income ratio for my 1980 car purchase. Intriguingly, we find that the ratio is not 1-to-1 as we once thought. According to our inflation-adjusted values, my 1980 car actually cost 120% of my 1980 income. Confused, we decide to rerun our calculations using different reference years. For example, we adjust the 1980 dollar values into 2024 prices, and then calculate the car's cost-to-income ratio. We do the same for the reference years of 2023, 2022, and so on, all the way back to 1980. When we plot our results, we find the pattern shown in Figure 9. The cost-to-income ratio for my 1980 car purchase appears to grow with time. History, it seems, can be steadily rewritten. Of course, this rewrite is a joke. In reality, we've been led astray by inflation adjustments, which are both unnecessary and invalid. Let's start with the unnecessary part. Just as we don't need to adjust for inflation when we purchase today's groceries using today's paycheck, we don't need to adjust for inflation when we compare historical transactions at the same point in time. Now to the invalid part. Why does inflation adjustment distort the relative value of my car purchase? Well, it doesn't have to work this way. The trick in Figure 9 is that we used two different price indexes, which, unbeknownst to us, give conflicting accounts of U.S. inflation. Let's have a look at this wrinkle in history. Figure 10 shows the historical movement of the U.S. Consumer Price Index, red, and the U.S. GDP deflator, blue. Until the late 1970s, these two indexes moved together. During this era, we could mix the CPI with the GDP deflator without creating much trouble. But from 1980 onward, our two price indexes parted ways, with the CPI rising much faster than the GDP deflator. During this post-1980 era, mixing the CPI with the GDP deflator became a statistical no-no because it provides a way to distort history. A past purchase that's tied to the CPI will appear to move relative to income that's tied to the GDP deflator. Artifact atop of artifact. Back to Pielke's work. When we left off, we'd seen how the billion-dollar threshold effect created an apparent downward trend in the average cost of natural disasters as a share of GDP. Apparently unaware of this effect, Pielke mistakes the downward pattern for something real. Now to step 2 in Pielke's error cascade. On top of the threshold effect, Pielke adds a distortion created by conflicting price indexes. He mixes the CPI with the GDP deflator, just as we did in Figure 9. To unwittingly achieve this distortion, Pielke's thinking might have gone something like this. Putting on our proper economist hat, Pielke's term, we see that the billion-dollar disasters dataset provides CPI-adjusted values for disaster losses. In the language of mainstream economics, these adjusted losses represent real monetary value. As such, we should put these real losses in a solvency context by comparing them to real GDP. While this comparison seems reasonable, the language of economics misleads us. The so-called real value inferred from the CPI is not the same real value that's inferred from real GDP. Under the hood, the latter data is indexed to the GDP deflator, which conflicts with the CPI. The result is that if we compare CPI-adjusted disaster losses to real GDP, we unwittingly rewrite history. Importantly, the effect of this rewrite is to bolster the apparent downward trend in average disaster costs as a share of GDP. Figure 11 illustrates the distortion. Here, the dashed line shows the trend in average disaster costs derived from nominal monetary data. See Figure 7. The red line shows the updated trend after the data is warped by our conflicting price indexes. Although the change is subtle, it is significant in the sense that it lowers our regression p-value below the magic threshold of 5%. According to standard statistical lore, our results are now publishable. Unfortunately, this reassuring p-value is, like the trend itself, a mathematical artifact. In fact, it's generated by multiple mathematical artifacts. To create the pattern in Figure 11, we start with the billion-dollar threshold effect, which generates an apparent downward trend in average disaster losses as a share of GDP. On top of this artifact, we then distort history by indexing the data to conflicting price indexes. The net result is that we've still said nothing about real-world natural disasters. As Figure 12 demonstrates, we can predict our downward trend in disaster losses simply by transforming the billion-dollar threshold itself. When we tie this threshold to the consumer price index, compare it to GDP, and then distort the results with price index shenanigans, out pops the apparent slope in our disaster data. Magic. A linear bed of Procrustes. It's at this point that our plotline gets weird. In his paper criticizing the billion-dollar disasters dataset, Pielke could have reasonably published a chart like Figure 11. And by reasonably, I mean that such a chart appears statistically valid. It plots a regression line that is a good fit to the data, and it reports a p-value that's in the correct zone. Of course, we know that these results are a statistical artifact, but the average peer reviewer, busy as they are, would almost certainly miss this subtle but severe problem. Inexplicably, however, Pielke chooses to go a different route and publish a chart that's both a mathematical artifact and statistically dubious. Figure 13 visualizes this twist. Here I've taken the data from Figure 11 and plotted it on a linear scale. By doing so, I've implicitly changed my trend line from being a log linear regression to a simple linear regression. This scale transformation creates several problems. The first is that the new linear regression is a demonstrably poor fit to the data. Visually, it looks bad, and we can confirm the poor fit by analyzing the regression residuals. See the appendix. Worse, the switch to a linear trend ruins our regression p-value, bumping it up to a non-publishable value of 0.09. Oddly, Pielke seems to have solved this problem simply by not reporting his p-values. Finally, the linear trend implies that average disaster losses will soon become negative, meaning disaster losses transform into gains. In this implied world, hurricanes hand out cash to their victims. Nonsense. Back to the running theme of Pielke's analysis. The effect of Pielke's inappropriate linear regression is to add a third mathematical artifact on top of his existing stack of errors. Let's review. We start with the billion-dollar threshold effect, which generates an apparent decline in average disaster costs as a share of GDP. On top of this artifact, we steepen the downward trend by distorting the data with mismatched price indexes. Finally, we force the resulting artifact into an ill-fitting linear trend. The effect is to take our curved artifact and warp it into a straight line. Figure 8 illustrates the cumulative procedure, which by now is quite convoluted. Still, the results say nothing about real-world disasters. They're entirely a product of our analytic method. Pielke's artifact stack. We're now ready to return to Pielke's published analysis of the billion-dollar disasters data. As shown in Figure 1, reproduced here, Pielke reports that relative to US GDP, average billion-dollar disaster costs have declined by about 80% over the last 4 decades. Having painstakingly tracked Pielke's method, we know that such a trend can be extracted from the billion-dollar disasters data. But we also know that this pattern has nothing to do with real-world disasters. The apparent downward trend in disaster costs is created entirely by a stack of mathematical artifacts. The billion-dollar threshold effect, distorted by conflicting price indexes, and then straightened by an inappropriate linear regression. Atop this artifact stack, Pielke's chart rounds things out with a few more errors. For example, it seems that Pielke misindexes his real GDP data. He uses data with the wrong reference year, thereby slightly inflating all the values in Figure 1. Pielke also reports GDP source data that's either erroneous or incomplete. His chart extends to the year 2022, but his reported GDP data ends in 2019. Finally, Pielke's chart mislabels the vertical axis. It should read percent of GDP, not billion USD. For my exhaustive replication of Pielke's work, see the appendix. Summarizing the whole affair, if Pielke's analysis of billion-dollar disasters was meant to parody his own appeal to scientific integrity, it certainly succeeded. Selecting for bad science. In my mind, Pielke's analysis of billion-dollar disasters is a good example of what Paul Smaldino and Richard McElreath call the natural selection of bad science. The idea is that doing junk science is not a conscious goal, but is instead a selection effect created by the pressures of the academic environment. Put simply, good science is marked mostly by ideas that don't pan out. However, the modern academic environment rewards the incessant production of hypotheses that apparently do pan out. Given this environment, scientists have two choices for survival. They can either get better at generating true hypotheses, or they can develop unwitting ways for transforming null results into something significant. Smaldino and McElreath argue that many scientists have opted for the second approach, which they achieve by unknowingly using bad statistics. Turning to Pielke's analysis of the billion-dollar disasters data, I think a similar effect is at play. Which is to say that Pielke's long list of errors was almost certainly unintentional. That said, I'd guess that the direction of these errors was not random. Let's put it this way. Suppose that a scientist is both error-prone and biased towards results which downplay the financial costs of climate-related disasters. In this situation, random errors get filtered by the storytelling bias. The result is that published errors tend to cut in a direction that bolsters the storytelling goals. In short, had Pielke's cascade of errors made it appear like average disaster costs were increasing against income, I'd guess that the results would not have been published. The lesson here is that when we mix error-prone analysis with a storytelling bias, we create a surprisingly powerful method for identifying quirks and loopholes in a set of data. On that front, the billion-dollar disasters dataset contains an unfortunate liability, which is the billion-dollar threshold itself. Simply put, this threshold makes unbiased analysis of the disasters data more difficult, and it creates unintentional artifacts that can be used to distort the actual evidence. In short, if the NOAA one day resumes tracking weather and climate-related disaster costs, it should abandon the billion-dollar threshold. At least then, there'll be one less artifact to exploit. Well, that's it for this time. If you want to support more free-thinking, data-driven research about big social issues, consider becoming a patron. You can sign up at economicsfromthetopdown.com/membership. And if you're interested in the data and methods behind the charts, you can find a link in the notes. Until next time, I'm Blair Fix.